Section 18.2, charged objects and the electric force. So it's possible to transfer electric charge from one object to another. Some materials work especially well for this. One example is animal fur and an ebonite rod. These are some ones that we found work really well. What you'll find is that it's always going to be the electrons moving, as mentioned in the last video, right? So the object that loses electrons is going to have an excess of positive charge, while the body that gains electrons has an excess of negative charge. So as we look at our animal fur and the ebonite rod, right, uh, the animal fur is here positive, so that means it's lost electrons. It has given some of its electrons to the ebonite rod that is now negatively charged. It's picked up some extra electrons. And this is an important concept. It touches on one of our conservation laws, the law of conservation of electric charge, that during any process, the net electric charge of an isolated system will need to remain constant. It's conserved. So we can't magically create charge or destroy charge. It always has to go somewhere. We can account for it in that way. Now, that's one important idea of dealing with charged objects. The other one is one you may already be familiar with, and that's the common adage that opposites attract. So if you have two charges that are the same, they actually repel each other. Like charges repel, unlike charges attract. So if we have a positive and a negative charge next to each other, they get attracted towards each other. They want to go towards each other. But if we have two negative charges, they can't handle it. So they're going to repel each other. Same thing with two positive charges. Again, they repel each other. So anytime you have two of the same charge, going to be a repulsion. Attraction is only when they're opposite charges. And this is an important thing for you to know, because as we get into the electric force, you're going to need to be able to identify the direction of the electric force, or directions, depending on all the charge configurations present. So you need to be able to look at two charges and know, okay, would the charge on the right experience a force towards the other charge or away from it? Is that in the positive or the negative direction? So that's something I want you to hold in mind. Now, we've talked some about charged objects, and I have a question for you. Why does a balloon stick to your sweater? I don't know if you've ever had this experience of having a nice wool sweater and you rub a balloon on it and it sticks. Well, PhET put together a nice little simulation of this, which I have linked here. But we can take a look at it as well. And I'm hoping this is something you have experienced, right? So we have a balloon that I can move around, very nice fuzzy sweater over here. And so if I rub the balloon on the sweater, then if I return the balloon, notice now it's drawn to the sweater. It sticks to the sweater. So why? What is going on here? Well, first we can think about our charges. When do we see objects move towards each other? When do we see the attraction? That's going to be when they're unlike charges, right? So that suggests that the sweater and the balloon have unlike charges. Well, we can take a look at that. I'll reset the scenario and we can show all the charges. So notice we have all the charges in the sweater, in the balloon, and even in the wall over here. And all of them are neutral, right? There's no net charge. If I look at show charge differences, there's no charge there. We'll go back to show all charges. Now, if I bring my balloon close to the sweater without doing anything, it's not immediately attracted. So that's not enough. But if we then start to rub the balloon on the sweater, notice what happened there. It picked up electrons, right? It took some of the electrons off of the sweater and put them on the balloon, so that now the balloon is attracted towards the sweater. And I could even rub the sweater more vigorously and pull more electrons off of the sweater. And so now, when I release the balloon from the midpoint, it's drawn more quickly. There's a larger attractive force there. And that's because I've created a larger net charge on each one. right? If I show the charge differences, the balloon is now negatively charged, the sweater is now positively charged. It's not that we've totally eliminated charges. There's still some of the balanced charges present, but the balloon has now picked up some of the electrons from the sweater. Now, one other thing to think about. We've said that the balloon is attracted to the sweater because of the charge differences, right? The balloon's a net negative charge, the sweater's a net positive charge. That makes sense. Now, what about with the wall? What will happen if I bring the balloon near the wall? The balloon's attracted to the wall too, but the wall is neutral. So why would the balloon be attracted to a neutral wall? Well, that's something I want you to think about as we're taking a look at this. And hold that thought. Please feel free to ask questions on it. But for now, I think that's a good introduction. We'll get to take a closer look at how charges can move in lab. So I'm looking forward to spending some time on that too. So hopefully now you know why a balloon will stick to your sweater. The answer is physics or static electricity. One cool application of this is e-ink, right? Electronic ink. This is what goes into Kindle if you have the paper-like reader. And it's super cool technology. What happens is that there's either a dark liquid or even dark balls, and then these white balls or beads on the bottom, and they have opposite charges. So if you put a positive charge on the bottom, then it attracts the white balls that have a negative charge, and that puts up a dark top to create a dark pixel in the display. You can do the same thing with somewhere you want to have a light pixel. You can put a negative charge, and that repels the negatively charged beads so that the white is what shows up. So this is really cool. There's a video that I did not put together, but I put it in the link so you can see some of it. Someone who toured the e-ink facility, this came out of MIT, really great invention here. And so, yeah, I encourage you to check this out. One of the real benefits of e-ink is that it only uses energy when you are changing the display. So when you're turning the page in your Kindle. Otherwise, it can keep displaying that without using any battery. So that's a really powerful application. It's also much easier to read for extended periods. There's a reduced glare. You don't need the backlight. So there's some definite useful applications to e-ink, and it's just taking advantage of some basic charge mechanisms of like charges repel, unlike charges attract. All right, we will see how we can charge different objects in the next video. So, hope you are getting charged up in anticipation.